Okay, so here's a fairly complicated rates of flow question. So we've got water inside the container, and this is an inverted cone, right? So it says the cone has an internal base of radius 2.5 meters. Okay, and a vertical height of 4 meters. Time t seconds, the height of the water is h, and the volume of the water is v meters cubed. The water is modelled as leaking from a hole at the bottom of the container at a rate of pi over 512 times the square root of h meters cubed per second. Right, so we've got to show that while the water is leaking, this is true. That's what we're going to try and prove. Okay, so first thing, we know that volume is equal to 1/3 pi r squared h. Okay, so what we're going to try and do is we're going to try and set a derivative. We want dv by dh. Okay, but we've got h here, but we've also got r. Now, the problem is that the radius is not constant. So what we're going to do, we're going to use the idea of a similar triangle inside our cone. Because even though the radius changes, the ratio to the height will stay the same. So we know that the ratio over the height is equal to the initial radius divided by the initial height. So that ratio for that triangle is going to be the same no matter where we are. So the radius is going to change as the height changes in the same ratio. So what we're going to do is we're going to take this and we are going to substitute it into our equation for the volume. So we're going to write volume is equal to 1/3 pi, and instead of r squared, we're going to put this. Now remember, we want just r, so it's going to be 2.5 over 4 times h. So 2.5 over 4 times h, and we're going to square that. So that means that volume is going to be equal to 1/3 pi 2.5 over 4 squared, and you'll see that basically it's an equivalent fraction that will come up as 25 over 64, or as shown in the mark scheme, 75 over 192. And we're going to need that fraction to get to this answer. Okay, so that's now times h cubed. Okay, so now we've got volume, and our volume is stated. The only variable we have is now h. So we can differentiate that with respect to h. So if we differentiate this, we'll have 3 times 1/3, so that's 1, times pi, times our fraction, 75 over 192, and that's just going to be h squared. So we've got dv by dh. Brilliant. Right. Now, we're also given the rate that the water is flowing out. That's our rate that's flowing out. So that is the change in the volume over time. So that's pi over 512 times the square root of h. Now remember, this is water leaving, so the volume is going down, so that's going to be a negative. So now I've got dv by dt and dv by dt. Okay, now remember we learned from the chain rule, you can see that dv by dt must be equal to dv divided by something times dt. Well, what's the thing that's linking them here? Well, it is our dh. Okay, so that's the thing that's linking them together. So now we know dv by dt. Now dv by dt is minus pi over 512 times the square root of h, dv by dh, we've just worked out up here. That is pi times 75 over 192 times h squared, and we don't know what dh by dt is yet. Okay, and that's basically what we want to get to down here. Right, so we're almost there. What we need to do is simplify this a bit. And as you can see here, what they're doing is basically they're well on their way to separating the variables to then integrate it. So we've got an h over here. Okay, we need to move that. We've got a fraction here. We need to move that. And then on both sides, we've got a pi, so we can divide through by pi. So what we end up with, okay, well, if I divide h squared by the square root of h, that's 2 minus a half. That means that I'm going to get h to the power of 3 over 2, 1.5. Okay, and I've still got my dh by dt. Okay, I've divided by the fraction, so that's gone. 1 over 512 divided by 75 over 192 comes to a very satisfying 1 over 200. And then I have got exactly what I want for part A. So that's part A taken care of. Okay, now, this is given the container is initially full of water, find an equation in terms of H and T to model the situation. So now this is where we want to integrate this, because we want to come up with a single model. Okay, right, so what have we got? We've got that. So let's integrate. So if we put an integral here, I've got an integral here. Okay. I've got 1 over 200. And I've got a dt that I'm dividing by. Well, all I have to do is multiply out dt. So now I've got h's on the right, t's on the left. So when I integrate this, I get, let's not put equals on that. I'm going to get minus 1 over 200 times t plus c, and that is equal to 2/5 of h to the power of 5 over 2. Okay, so that's that taken care of. Now, what I need to do is I need to work out what c is. So I set my initial condition. My initial condition was that when t equals 0, h equals 4. So therefore, I can substitute that in here, and that tells me that c is equal to 64 over 5, because that's the only unknown. So therefore, I can find c. So now I know. We'll rub that out. Now we know that this is 64 over 5. Brilliant. Okay, so there we go. Now I've got taken care of part B. That's in terms of H and T for this model, there's no C. Now H and T are the only unknowns. So part C, it takes approximately 43 minutes for the container to empty. Use this information to comment on the suitability of this model. Well, okay, so what do we need to do? We need to compare this 43 minutes to the answer from our equation. So if the height is equal to 0, that means that our container is empty. So if we do that, this side is just going to be 0. And this side is still going to be 1 over 200t plus 64 over 5. So all I've got to do is rearrange this to work out what t is. And I find that t is equal to 2,560 seconds, which is equal to 42 minutes and 40 So it's pretty close. So therefore, it is suitable. Okay, that's all I have to say. The result is close, so my model seems suitable. And that's that.